Hey folks, our model today is continuing the use of differential equations, and this time we're going to describe how we could determine the dosage required of some drug that will maintain an effective level of drug in the body, but at the same time keep that level of drug safe. So suppose that you need to take a regular prescription pill and you want to keep the amount of drug in the bloodstream, because that's how it's delivered to the cells and things. You want to keep the amount of, or the concentration of blood in the of drug in the bloodstream at a safe and effective level. And as you brainstorm the kind of things that might be important in this, things might include the assimilation rate, how quickly the drug is absorbed by the body, how quickly the drug is cleaned out of the body by the liver and kidneys, or I don't know, whatever does that work. What also might matter is the volume of the person, the body weight of the person who's taking the drug, the amount of the drug, there's obviously an interval between the times you take the drug. So there's lots of variables is what I'm saying. And I'm going to concentrate in on two submodels. I'm going to build a submodel for assimilation of the drug. In other words, the uptake of the drug into the bloodstream. After you take a pill, how does the drug end up in the bloodstream? I want to model that. And then secondly, I want to talk about how quickly the body removes the drug from the bloodstream. So we're going to build those two submodels, and from that we can build this overall model for drug dosing. So before we make progress, we need to introduce a few variables. I'm going to call C of t the continuous function that gives us the concentration of the drug in the bloodstream at time t, and I'm going to imagine that this is measured in milligrams per centimeter cubed, which is a fairly typical kind of unit for concentrations. And then I'm going to define two variables, h and L, where h is the highest safe concentration of the drug in the bloodstream. Presumably anything above that level can cause damage, and so you want to avoid being above h. And also L is the lowest effective concentration, so if you're below L, the drug's not doing anything, and so you want to stay above L. So what that creates is an envelope where we want the concentration. If we want the concentration of the drug in the bloodstream to be above L and below H, then we're going to have it somehow oscillating in here perhaps. So that's our job. We want to find what that function is. The Y value here is the concentration with time. And L and H are going to be given to us by some sort of experimental trials, right? This is why they do drug trials. So experiments will tell us what L should be, what H should be. So we'll get that data from the trials. So thinking about our two submodels, the first is the decay of drug. So imagine you took a dose of the drug and then your body slowly removes it. So it's reasonable to assume that a certain percentage is removed over every period of time. So every day you lose 10% of the drug. If your kidneys or liver or whatever are acting like a filter, and then they're kind of straining out a certain percentage every time stuff flows through them, you'd expect that to be the kind of way it would work. So if we assume that the rate of removal is proportional to the amount of drug that's present, we're saying that the rate of change of C, the concentration, is proportional to C. And I'm going to call that proportionality constant K. And just to make sure that it's clear this is a decrease, right? The drug's being removed, so this is a decay, a negative rate of change. I'm going to put that negative out there. So this constant K is the elimination constant. And K is positive because I've chosen to explicitly put the negative sign right there. All right, so this is a rate of decrease, and and then K is the fraction. So, for example, if I told you there's a 2% decrease per day, and T is in days, then K would be 0.02. Okay, so it's literally the fractional rate of change. And the solution of this we know, because this is exactly the differential equation that we set up to solve in the previous section. And so I'm just going to write down the solution. We had a P last time. This time I'm going to call it a C. But apart from that, and there's a negative sign instead of just a K, it's a negative K. But it's exponential decay. This is an exponential function that's decaying with time. So if we think about how the drug is behaving in your body, after we start with some amount, some initial value C0 at time 0, this is just going to decay exponentially down towards 0. right? So our assumption here led to a differential equation, but the differential equation itself is very, very straightforward. We've solved it before. It just gives us this exponential decay. So our decay model has come down to the amount of drug in the body decays exponentially. So again, here's the summary. The amount of drug in the body decays exponentially, and I can write that in another way that's going to come in handy later. Notice that we start with some value C0. When t is equal to 0, e to the 0 is 1, so we just get C0. So after that initial amount of drug, right, C0 is the initial concentration in the bloodstream after you've taken a dose. Think of it that way. So after you've taken a dose, somehow the amount of drug in the body ramps up until it's at a maximum, and then the body starts cleaning it out, right? How it ramps up is what we'll talk about next. That's our second submodel. But what we've talked about so far is the decay. Now let's suppose we take a dose every t units of time, right? So at time 0 here, I take a dose, and then at time capital T later, and I called that an x, but really it's a t, that's the time variable. So at some time later we take another dose. So at this point something else happens because I've taken a new dose. So this piece isn't interesting. But what is interesting is how much of the drug is left in your body at that moment, right? At the moment where you take the next dose. So before I take the next dose, there's going to be some residual amount of drug in the body. And so I can kind of see what that's going to be. This is C as a function of big T, and it's going to be given by this. And notice all I've done is plug capital T in. So I've just plugged capital T into this formula. I get C0 e to the minus kt. C0 was the concentration that I had at the beginning, after I took the drug at the maximum before it started decaying. So this is the concentration when I took the dose, and then you multiply it by that factor, e to the minus kt, and that will give us the value here. And then presumably we take another dose. So let's come back to this, but let's look at the assimilation model. And that's just a fancy word for how quickly the body takes up the drug. And I'm going to make the simplest assumption we possibly can, because our job is always to do things as simply as we possibly can. So my assumption is the moment you drop that tablet on your tongue or take that injection or whatever it is, your body immediately takes all of the drug and distributes it equally in the bloodstream, and it's instantaneous. It's a ridiculous assumption, but it makes life easy. So put another way, if we administer the drug at time interval t, a fixed time interval, so every t, capital T, seconds or hours or whatever we're talking, we're going to give this drug, then it results in an immediate increase in concentration in the bloodstream by the amount C0, because that's the value we were using before, so let's just use that value. That's the result of taking this drug once. Every time we take the drug, it increases the concentration by an amount C0, and I should have said milligrams per milliliter before, not centimeters cubed. I think they are the same. The important thing is this formula tells us how it then decays. This rule, here's our assimilation. If I'm going and I've never taken this drug before and I'm just cruising along and I wait for a time t and then I take the drug, what's going to happen is I'm going to have an instantaneous increase in the concentration in my blood by an amount C0, and then it's going to decay exponentially, right? So I'm going to have, this is the moment I'm taking the drug. This is the exciting moment when the drug is taken, and I'm going to have an immediate increase of C0 in the concentration in my bloodstream, and then it's going to start decaying away. And then we see that it probably won't decay away, and it can't decay away completely before we take the next dose, because this exponential never actually gets to 0. And so this is an exponential decay, but it won't reach 0 before we take the next drug, or take the next dose. And so what's going to happen is the drug is going to decay away to some level, and then I'm going to take a new dose. But our rule says that the amount jumps by C0 every time. So this is time 2t, right? Another period of time t has passed by. So every time a period time t passes by, I'm going to take a new dose. Now the concentration wasn't 0 to start with, so this is going to be C0 plus whatever it was here, because there was some still in the blood, right? And I've started this at t, but really I'm going to start it at 0. So let me go and set this whole argument up. So you can see what happens here is I took my initial dose at time equals 0. This is a bit different than the way I set it up in the previous page. But remember, our goal is to take a dose every t amounts of time. And so I've started here with my initial dose at t equals 0, which means I'm ready to take another dose at t equals, well, small t equals big T. This is exponential decay, right? The idea here is that we take the initial dose, and that leads to it leads to instantaneous uptake of concentration, and then we decay that concentration exponentially. And then at time capital T, we take another dose. And there we go. We took another dose. And the dose results in an instantaneous increase in the concentration by an amount C sub 0, which gives us a value that's above the original dose, right? So this slowly increases because all of the drug didn't decay away before you took the next dose, which is what you want, because we want to actually maintain a decent amount of drug in our body. So we don't want it to all decay away completely. So I'm going to call this the residual. I'm going to call this R1. This is the residual amount of drug in the body when time is big T, which means then I'm going to take another dose and instantaneously increase to this value. So the value up here must be R1, which is what it was before I took the dose, which was C0, which is what we were left with. So now let's do that again. There we go. I let it decay away again until I got to time 2t, and at that moment we took another dose. So if I call this the second residual, right, the second residual is going to be there somewhere. It's hard to mark them on the axis, so I'm just going to write it here. And then I took a dose, well, that increases the concentration by C sub 0, so this is the second residual plus C sub 0. And then we take another dose. Sorry, we took a dose, and then we let it decay away before we take another dose. And the amount left after it decays is R3, the third residual, the third decay period, and then we take the fourth dose. And the fourth dose takes us up to here. So this is the residual plus the concentration. And then we continue. And that gives us the fourth residual, and so on. So I think you can see how this is going to behave. Now, if I waited a long time between doses, in other words, this gap was quite big, then the amount of decay would really be quite significant, and we would have a really small amount of drug left when we took the next dose, right? If you waited a really long time between taking doses, then it's going to decay a lot, and so you'll have very little left. I'm showing something here that's a bit in between because it looks like the way I've drawn the picture, I've only decayed away around, what, a half or 2/3 of the drug here before I take the next one. So there's a significant increase from one tablet to the next. And so what we want to do is work out what happens in the long term. Well, let's start giving these things names. If this was C0, that was our initial dose and also the jump from dose to dose. I'm going to call this maximum there C1, and this one C2, and the next one C3, and then I'm going to work out what they are. Obviously, C1 is going to be R1 plus C0. But what's R1? Well, on the previous page, we said that the amount that was left here after a time t, and remember that's our R1, is whatever we had at the beginning, the concentration when you took the dose, multiplied by e to the minus kt. K is the decay constant of the drug. We're going to get that from experimental trials. Someone's going to tell us. And capital T is the amount of time that's passed. So R1, in this case, must be C0 times e to the minus kt, because we started with an amount C0 and then we decayed down for a time t. And so that lets us fill in what C1 is. So this is C0 e to the minus kt plus C0, right? Which we could rewrite by factoring out the C0 if we like, and write it as e to the minus kt plus 1. Beautiful. But then what's C2, right? C2 is clearly going to be, well, it's written right there. It's R2 plus C0. So the residual here, this residual, plus the extra dose. Well, what's this residual? Well, the second residual has to be, looking at this idea again, the second residual here is what we get when we start with this amount and we let it decay down for time t. Because we start at time t and we ended up at time 2t, so that time interval there is capital T. And we started with the amount C1. So this has to be C1 e to the minus kt. right? In this first case, for R1, we started with this value here as the initial concentration and then let it decay. And here's the rule for how that works. Well, this time, we started with this concentration there, and we multiplied it by that factor, which is the decay factor. So I know what C1 is. I just calculated it. So this is C1 e to the minus kt plus C0. So I've just cut and pasted the things on the previous page onto this page. What I want to do is build up this list of residuals a little bit. So the third residual, let's think about that. If we go back to the picture, we can see the third residual is going to be what we get from decaying the concentration C2. And the fourth residual is going to be what we get decaying the residual C3. And the fifth residual, the concentration C3. The fifth residual is going to be the decay of the concentration C4. And so we can kind of build these things up. This is going to be the second concentration, e to the minus kt. This is going to be the third concentration, right, after we take the third dose, and then we decay it. So we can sort of reconstruct these things because on the other side, we've got an expression for the C's. So C1 e to the minus kt, we've got that here. So we're going to end up with here C0 e to the minus kt plus 1. And we're going to multiply it by e to the minus kt. So I'm looking at this quantity now. This is C1. And then I've taken C1 and I've multiplied it by, oops, no, that's not true. C1 is this. This is C1. And I've multiplied it by e to the minus kt. Right? And then I've added C0. So you can start writing that out. This is C0 as a common factor. Though multiplying the exponentials, you'll get e to the minus 2kt, and then you'll get plus e to the minus kt, and then you'll get plus 1. And then we can build C3. Well, C3 is going to be the third residual plus another dose, right? Because we go over here, C3 is up here. It's the third residual right there, plus the dose C0, the instantaneous uptake. And so when we write that out, we're going to get C0 and R3 I've got up here. And R3 depends on C2. So let's start writing out this side. I've already calculated R2. No, I haven't calculated R2. R2 is this term, C1, multiplied by the exponential. So notice that it's always going to just increase the exponential by 1. We're going to get e to the minus kt plus 1 times e to the minus kt. Again, this quantity is C1, and I'm just multiplying it by the exponential. So it just decays it down. So this is C0, if you like, e to the minus 2 kt. If I multiply that exponential in, e to the minus 2 kt plus e to the minus kt. There's our R2. So C2 is then C0 e to the minus, and taking C2, if you can see what's going on here, taking this whole quantity and multiplying it by the exponential is just going to raise every one of those powers by 1. So what was an e to the minus 2 kt is now going to be 3, and then we're going to have a 2, and then we're going to have a single e to the minus kt. And if you follow this pattern, R4 is going to be, well, here we had the second one had the second and the first power. This just had the first power. So R4, you're not going to be surprised if you work it out, is going to come from down here. R3, I just calculated that. If I pull a C0 out of all of this, right? So I'm pulling a C0 out of all of these terms. So there's one C0, so I'm just going to write a plus 1 on the end. And then I've got R3, and I just worked out R3, so I'm just going to write it down. It was e to the minus 3 kt plus e to the minus 2 kt plus e to the minus kt, and that is all from R3, and then we added a single R0. And so R4 is just all of that multiplied by another power of the exponential, which takes it up to 4, right? And then there'll be a 3, and then there'll be a 2. Right, so I'm multiplying C3, so I'm multiplying all of that by the exponential, and then there'll be a 1. And so you get the idea. Hopefully you can see that Rn, it seems reasonable, is going to be C0. The fourth one had a 4 there, the third one had a 3 there, the fourth one had 4 terms, the third one had 3 terms. This is going to be e to the minus nkt plus 1 less e to the minus, well, n minus 1 kt, all the way down until we run out. So there's the final ones. So it's going to start with e to the minus nkt, and it's going to go all the way down to 1 lot of kt. So there's our c sub n, our r sub n, and c sub n is similar. If the third one had up to the third power but included the 1, it's going to be almost like this, but it's going to have the plus 1 there. So the third one starts with e to the minus 3 kt, the nth one starts with e to the minus nkt. We've got these formulas for what happens after n doses. And if I know what happens after n doses, I can do exciting things like take the limit and find out what happens after an infinite number of doses. So let's step back and think about what we've got here. We took our first dose here at time 0, and then our second dose at time 1t, and our third dose at time 2t. And so at time nt, we're about to take our n plus 1th dose. So our nth dose has decayed away to this value. This is the concentration R sub n. And after we take the n plus 1th dose, we're going to end up with this concentration. And so when we're taking a pill regularly, what we're interested in is what happens in the long term, right? We're not interested in what happens after the first 3 doses. If a doctor prescribes you to take a pill, 3 times a day for 3 weeks, the first 2 doses aren't very interesting. It's what happens as you settle into that regular pattern. And so we're going to think about this nth dose, and we're going to take the limit as n goes to infinity. So we're going to see, is there any particular pattern going on emerging in the long run? Not at the beginning, because at the beginning, it's not that interesting. And at the beginning is what we tend to call the transitory information, because we'll often see things at the beginning that kind of disappear in the long run. And we'll see more of that as we talk. Let's introduce some notation. I'm going to start using the symbol r to be e to the minus kt because it makes my life simpler. And I'm going to think about what r sub n looks like. R sub n, if I factor out an e to the minus kt, then what's left of r sub n is going to be, well, 1 less than n here, and there's going to be 1 of them there. I need more room. You see, I factored out 1 of them here and 1 of them there and 1 of them there, leaving e to the minus kt, and 1 of them there, and I wrote it out the front. And now I'm just going to write all of that in terms of r because it's a lot easier. This is going to be c sub 0 r times, well, r to the power of n minus 1 plus all of the other integer powers down to r to the power of 1 plus 1. So I'm using this symbol for r, I'm just replacing the exponential, and we end up with this expression for r sub n. So let's look at what we can do in the long term now that we have that expression. I've rewritten it here, and notice that if I pull out one of those r's, which I had on the previous page, then this thing in the bracket, we've already calculated that when we were calculating the limits for the in chapter 1 when we were looking at the linear discrete dynamical systems. We ran into one of these geometric series and we summed it. Remember, the sum is 1 minus r to the n over 1 minus r. So I just plug that in. And so we can then rewrite that to give us r sub n in a much simpler form. Just substituting back in what that small r variable was, we end up with this. And notice only one of these terms involves n itself, right? N is how many doses we've taken. This is the residual after n doses. And so everything else here does not involve n at all. So I'm going to define the limiting value of r sub n. I'm going to divide it to be big R, and it's the limit as n tends to infinity of small r, right? The limit as n tends to infinity of r sub n. Then r must be identically the same, except we have to take that limiting term. We have to plug that value in. And if you think about n and k and t, they're all positive numbers. So that's a decaying exponential. That's an exponential that looks like this. So as n goes to infinity, this is a decaying exponential. The limit is 0. And so we have our final form for r. R is just going to be c naught e to the minus kt, that factor out the front, times 1 minus 0, divided by that factor in the denominator. And I could simplify that further and write it as c0 over e to the kt plus 1. If you wonder where that comes from, think about multiplying this top and bottom by e to the kt. Just a little bit of algebra will leave us with this final form. And so that's our residual in the long term. After an infinite number of doses, the residual actually settles down to a fixed value. So let's think about what that means. So we'll have a look at a picture. All right, so what we've seen here is that in the limit of these residuals, as n goes to infinity, we get this fixed finite number. And I obviously made a mistake on the previous page. That's got to be a negative. I fixed it. That's definitely a negative. It was a negative there. I can't change that negative. But we get a fixed finite number for these residuals as n tends to infinity. And that means that our residuals settle down to a finite value. Look at the residuals on the picture. There's R1 and R2, and here's R3, remember, but there's Rn plus 1, and so on. Eventually, those residuals are getting closer and closer to R. Those residual values are sneaking up on this number R, and I drew that R as a purple line. That's the limiting residual. Eventually, what's going to happen? Well, the only choice is eventually we're going to get a curve that's just bouncing up and down to that residual. So if you imagine continuing this for a very long time, we're going to get something that starts looking like this. Look how the residual here and the concentration, and then the residual and the concentration. Eventually the residual is just coming, the nth residual is just starting to really just approach that long-term value R. And then it bounces up because we took the drug. Well, if it bounces up, and I've got to move that, if it bounces up, how far is it going to bounce up? Well, taking the drug creates an increase of C sub 0. So this must be R plus C sub 0. So eventually, we're just bouncing between the residual value R and R plus C0. And then the residual value here, and then R plus C0 again. So in the long term, the drug just settles down in your system so that it never really drops below that residual amount, but it never rises above that residual plus the effect of one pill, because this increase is the effect of taking one pill. So that gives you an idea maybe of what this model is telling us. I'm going to leave it there today. I think that was complicated enough. There was lots of algebra and stuff involved, but try and concentrate on the big picture of what's happening here with the model, what the math is telling us, because that's really the whole key in this course. What's the mathematics telling us? And this is quite a complicated algebraic model, but it's the outcome that we get from the mathematics that is important, what we can see about the situation. So we're going to talk more about that in the next lecture. You have a great day. Thanks for watching.